Here's the outline. We'll start with some general concepts of our project, dive into details with the software hardware, along with some tests, and then we'll conclude with some budgets, the demonstration, and some standards and applications. To introduce ourselves, I'm Tony. I'm the project manager. I'm a computer engineer and part of the software team.
I'm Ronnie Arbonite. I'm a software team member and a computer engineer.
I'm Yetan Ayete. I'm part of the hardware team and electrical engineer.
So we were motivated to create a system that allows customers to check out of the store much more effectively. Especially during the holiday season, stores get backed up quite often with long lines, especially retailers such as Walmart and Target, very big retailers with a lot of customers. So we wanted to create a system that was superior to the modern solutions. For example, Amazon Go has a few stores where you actually walk in and then you walk out with all the products you have based on computer vision with cameras all over the store. And Panasonic Robotic Checkout also has a very complex machine, and it's a self-service machine that does the checkout process for you. But they prove to have a lot of disadvantages, such as cost, power consumption, and size. So our design aims to improve on those disadvantages and incorporate the phone, which almost all of us have.
For our product description, our design must provide customers in the retail environment a smooth checkout process that could be efficient and quickly, with using only their phone and items they wish to purchase. Our system will scan the user items and send the transaction information to their phones and allow the users to complete the purchase with our mobile application. Each transaction is saved to the user's account, where they'll be able to browse past purchases and the products that are available in the store. Our system will impact the way people check out by providing a faster and more convenient checkout process, allowing customers to spend less time in the store and manage their purchases with ease, and also allow business managers to manage their inventory and product reviews. It will also allow businesses to serve more customers using less power and less labor. So basically, this is our project in a retail environment. This is one of our systems. So basically, a store can have up to 4 or 5 of these systems in their store, how many they want basically. So basically, we have the RFID antenna that's going to be above the customer, so they'll be able to easily push their cart underneath the antenna so it can scan all the items. And also the NFC card emulator will be in like the middle of the post, so customers of all sizes can easily access it to scan with their phone.
So on the left-hand side, we have the customer, which in order to engage with the system, it needs a smartphone and at least one product. It's important to know that the system is smart enough to recognize if the customer has an item in their cart or not, and if it doesn't, it just let the customer pass without charging them. If the user has a product in their cart, the RFID reader scans the product. It sends it to the Raspberry Pi, and the Raspberry Pi encodes the product inside the NFC, which subsequently the user scans. It sees the products that he has in cart, and it gives them an option to either purchase the products or return one of them. This is the hardware. On the left-hand side is the NFC BN532 chipset. That's what we use to store the unique identifier, which identifies every product. And on the right-hand side is the RFID reader that collects all the products in the user's cart. In terms of the software, the hardware is completely coded in C, including both RFID and the NFC. In addition to that, the server that connects the two is written in Python, as a Python script that listens for the changes in a text file, and that text file contains every product that is in the user's cart in a uniquely identified number, so each number is stored there. For the mobile app, we use Swift, is a native programming language developed by Apple. And for the IDE, we use Xcode. As far as the database is concerned, we use Firestore, Google database. And for the designing prototype, we use SketchUp. This is a code snippet. So once written on Swift. So once the user has the whole script runs on user's phone. So you have a function which is run asynchronously, which means it waits to get the data from the database, and it doesn't continue, meaning it doesn't show them what products they have purchased unless it gets all the data from the database. And each product is tokenized, each SKU number, each identifier is tokenized, and it's passed into a function which makes the call to the database and gets more information regarding that product, including the price, product name, the description, image, so on and so forth. So this is how the app looks like. So once the function is completed, it shows the view on the left-hand side, the products, the total, and it gives them an option to pay for the products that they want to purchase. In the middle is the inventory. All the products inside that store are categorized based on categories of toys, food, sports. On the right-hand side, there's an example of how the products are listed. And we can also see that there are, it shows how many items are in stock. And once the user has purchased, it updates the database and it shows one less item depending on which product the user has purchased. We'll see that in the video.
So we did some unit tests this semester. Once we got the entire system loaded and ready to scan for items, the first thing we did was test for the range of the antenna. Exactly how far can a customer be before it starts misreading tags or not reading tags at all. So what we did was we did 10 different reads of 10 tags and did the average of them at different ranges. So around 2 to 8 feet, we have about 7.8 to 7.5 average, and then it slowly dips down from 10 to 18, and then it really dips down after 18, which was supposed to be expected because the antenna's max range was 18 feet. So what we noticed here is that in a lot of the cases, it didn't pick up all the tags. And it wasn't so much the range because at particular stages of this graph, it's steady for a bit, but at no point did it get all the tags. So we did another unit test. What we did was we put the tags on different types of materials, pieces of paper, cardboard, on water bottles, on food, different types of merchandise, and tested the read rate at a fixed distance. So for this graph, we did it at 4 feet and did the same thing, 10 tags, 10 reads, the average of those. And we found that the antenna performs best on pieces of paper and cardboard pieces, but it drastically steeps down once you put it on water bottles, on fruit, on candy bars. Something about the material not being able to reflect off it properly with the EM waves and not perhaps sending enough current through the wave causes some issues as to what tags the items can be on. But as for the integration test, which we did toward the end of the semester, we organized the entire system together to see if it all performed as intended together, and it passed. The system successfully scans the tags that can in the range, saves the results to the Raspberry Pi, and prevents duplicate reads with an algorithm we developed this semester in the Arduino. Sends it to the NFC, and the NFC encodes it. Then the phone successfully reads the items and organizes them in an organized fashion. As for the acceptance test, since we had issues with some of the tags not reading particularly well at particular ranges or on particular material, we weren't able to make sure that all the tags were able to be properly read. But on the other hand, we made sure that whatever tags we could read were not read twice, using the unique IDs on the tags. We made sure the items are correctly added to the cart on the phone. We made sure that the entire checkout process was quick and easy. And
So for project completion and future work, while working on our project, we overcame many challenges. Our biggest challenge was actually developing the hardware, implementing NFC and with implementing NFC within the iPhone. We also learned many lessons. One lesson in particular we learned is that the NFC technology has recently been added to smartphones, which Apple actually just unlocked the feature in iOS 11 in 2017 for developers. Previously, it was only unlocked for Apple Pay use, so now they actually unlock it so other developers can actually implement NFC apps within the iPhone. And another thing we learned is even though the technology exists, doesn't mean that every device can use it. In our case, it was the iPhone and NFC, where in Android, the NFC technology operates in like 4 different modes: read mode, write mode, peer-to-peer mode, and card emulation. And Android can do all those modes, but iPhone can only read tag, so it will only operate in read mode. Another thing we learned is that new technology doesn't have that much documentation. So since Apple just unlocked the NFC technology, there wasn't that much documentation on how to implement it into an app. And since we had so much trouble implementing NFC into working with card emulation and NFC into the iPhone app, we weren't able to add the payment options such as Stripe, and also we weren't able to add machine learning, which we would like to for like recommending products and stuff. For refinements, we would want to create a casing for our product to make it look more production ready. And another thing, we would like to purchase a more expensive RFID reader, or maybe multiple RFID antennas to improve the read rate of the miss rate of our system.
So this is going to be our demonstration video. We're going to show you both sides, the entire transaction process from the view of the phone and also from the view of the customer. So first here we're going to show you a category. We're going to look at a category and you can see the inventory, but we're going to look at particularly 4 items here. We're going to look at particularly 4 items that we're going to use during the transaction. So keep note of the amount we have in the store here. So we have 4 items here, and in the ideal case the antenna will scan all the items, and it will send the SKU information to the NFC, where the customer simply taps their phone on the NFC, sending all the items onto the app, where they can then pay. Alternatively, after checkout, they can also refer back to the category and see that the inventory has changed as well. So it's good for inventory checking and for customers to know if the product's actually in the store as well. As for cost, although expensive and more above budget at $410, we were able to use the $210 M6E Nano chip that was already provided to us from a previous Capstone group. But the point of this graph is to show that the cost of expanding this system isn't very linear, because the more products you have in your store, the more tags you need. And in this case, tags are pretty cheap at about $1. It can be found even less. So even though it seems a lot at first, you can expand this system. You can find it to be economically viable to expand the system.
For standards and constraints, so for standards, we use the NFC standards, which uses the NDEF format and the Type 2 tag for card emulation, which transfers data between the card emulator and the phone. For the RFID standards, we use the UHF Gen 2 standard, which uses the bandwidth of 860 to 960 megahertz. We chose to use UHF because it allows for a higher read rate and the distance is the longest. And for the antenna standard, we made sure our antenna was FCC regulated. For our constraints, we had 2 main constraints, the NFC constraint and the RFID constraint. For the NFC constraint, we had a constraint with the iPhone because the iPhone can only read tags. So we had to use card emulation and for the NFC, and on our app we can only read tags. Whereas if we were using Android, we would use peer-to-peer mode to transfer the data. And another thing was the NFC tag data limits. We had to make sure what information we wanted to put on the tags. So we chose just to put the SKU numbers on the tags, not like the product stuff. We would just get that from the database. Another thing is the NFC read distance, which operates at a maximum 4 centimeters. And another constraint, another constraint was the RFID constraints, which was the read distance, which depends on our antenna and the tags you use. That's why we chose to use UHF. And with our antenna, I think it's up to 18 feet, so it's plenty of room for us. Another thing is the RFID data limit on the tags. So we only chose to put the SKU numbers on the tags, not like the product information, just the SKU numbers. So basically, when we run it to the app, we just use a SKU number to look it up in the database. For our ethical issues, our first ethical issue was security, which we wanted to make sure the database was secure with access control. Another issue we had was privacy. We wanted to make sure that the user data is only accessed by our system and no one else. And another ethical issue was the health effects of radio frequency, which we wanted to make sure that the RFID antenna is FCC regulated, so the user is not exposed to a large amount of radio frequency.
And here are references. I'll take any questions you guys have. RFID is a little more convenient than the barcode, because with the barcode you would have to scan each item one by one. So we found that to be very time consuming at the checkout line. So our idea with RFID was to have all the items in a single area where the customer didn't have to take them out. And you could just simply stand under read area and read all the tags. That's why I went with RFID.
Sorry, I just want to add something. That's a very good question, because I just want to explain what it means for why the RFID failed and what it really means. So with the benefit of the hindsight, I can really see why Amazon spent so much money into cameras and sensors. So with the RFID, even if we had a better antenna, that doesn't mean that the whole system would work better. It just means that the technology is not fit for what we're trying to solve. So with Amazon, the downside is that if you pick the product and you leave the store and you don't return the product exactly where you picked it up from, it won't recognize that you returned that product and it's going to charge you. That's why we decided to use the RFID. But unfortunately, it didn't work as we expected it would work.
Yes, Professor.
Do the items have to be placed in a cart to be scanned? Is everybody expected to have a cart for their items?
No, not ideally. You can walk in with the same bag you walk out with, just with the items in it. So ideally, what we were trying to test for was you could have the bag on your side, have the bag with you. The idea was you could have a reusable bag, fill it with items in the store, and just walk out without having to go through reusable bags or anything.
There's no problem about one item blocking another and not having one underneath or something being read. Is that a problem?
There were some problems with an item being in front of another. We also found that there was very unique cases where if you stimulate the tags in a way, such as like moving around or dancing under the reader, you'd catch more tags. So there are definitely problems with tags being in the way, but it was especially a problem with what material the tags were on. So,
Worked out.
for sure, yeah. Any more questions? Thank you again.